Hi guys, this is Brad. I made my mind to make this kind of video to solve two problems in one shot. The first problem that I've always wanted to solve is about speaking English. As you know, I'm not a native speaker in English. I'm just, a normal person who tried to be good at speaking English. So I might make some kind of mistakes or some, misusing pronunciation or something. But, it will be better one day. So I'm trying to. The second problem that I've always wanted to solve is about solving problems. You know, I'm not a super genius about solving problems. I'm just, like normal dude who like to solve problems. So if you are like a normal person like me, you can follow me. We could go somewhere together and we could achieve some kind of level in Codeforces or whatever the program is. And one of the purposes that I've wanted to achieve by making this kind of video is, communicating with people like me. If you, if you are stuck at some point about solving problems or speaking English, we can go together, we can communicate and we can solve, each other's problems together, and that will work. So let's get started. So we first start to solve XOR mixup, and it's about bitwise XOR. As you can see, there were n-1 integers from A1, A2 until an-1, and they made X, and that was made from bitwise XOR of all elements of the array. So, and then they added X to the array of A. So and then they shuffled. So I call it as array B because they, shuffled. So now we have, array B and we need to find what was the X. So, and an integer N was not that big because it's only 100 and the range of AI is up to 127. So it's so small. And we can find the answer by iterating all elements of array B. So we can assume that B1 is X. So except B1, we use bitwise XOR for other values from the array. And then we get the result, and I call it R. And if X is same with R, and the answer is B1, because we accepted, when we were, doing bitwise XOR. So B1 is the answer. So we can do this like B1, bitwise XOR, B3 until Bn, as we assume B2 will be the X, right? So we got the result for these bitwise XOR, and if X is same value with R, B2 will be the answer. So that's it. Let's have a look on problem B. The name of the problem is Rising Sand, and it's about finding total. We call it total if AI is strictly greater than the sum of AI minus 1 and AI plus 1. We call the AI is total. And we can do any number of operations on the range of k And then, we can maximize the number of totals. So we need some kind of observation to find the best solution. So I started to use k is equal to. So the array A can be like this, A1 from A1 to A7, because we need to maximize the number of total, you know, the totals that already total is no need to change. So I can assume the array can be this graph, A1, A2, A3, and so I can use k is equal to on this first rectangle, and it wrapped A2 and A3. So if I use the operation on this, the range in effect to A2 and A3, what can be changed? And it was about A2 and A1 plus A3 that decides A2 is too tall or not. And if I add 1 to A2 and A3, the equation can be changed like this. But it's all same because the plus 1 can be deleted on both sides. So there's no need to use operation on this section. So I tested with this rectangle, and A5 and A6 is affected on this rectangle. So A6 is decided whether it is total or not by sum of A5 and A7. And if I use the operation, the equation can be changed like this. But there's no change because it added on both sides. So if I use k is equal to 2 operation, there's nothing changed. So I tested with k is equal to 3, and the graph can be like this: A1, 2, 3, 4, 5. So the A2 and A4 can be totals or not. But so I added 1 on this rectangle, and it affects to A2, 3, 4, and there's nothing changed, you know. So now I know that adding any number of value on the range of k, it cannot affect about total, except when k is equal to 1. When k is equal to 1, we can add any number of value on any indices. So we can change it to be total. So the answer can be n minus 1 divided by 2. We can make, the maximized total numbers by adding any operations on k when k is equal to 1. And except that, the total won't be changed because the operation, won't affect anything on the array of, checking the totals. So the answer is quite clear. When k is equal to 1, the answer will be n minus 1 divided by 2. And except when k is equal to 1, the answer is, already decided by the array A. And that's it for the problem B. Let's have a look on third problem, threesome closer. And all we need to find is, whether the array A is fitting or not for the equation. And the equation is for all indistinct indices ijk, ai plus aj plus ak should be al. So, any indices should be working on this equation. So we need to check. We need an observation how to check. So I wrote down some integers. let's have a look on negative integers. So there are -7, -5, and -3. So I call them ijk, and AL should be -15, and because it's not in the array, the answer will be no. So what if I make this, array as yes? So I add -15 here, so it's working, the equation working. But what if I call -15 as j, I, and j, k? The AL should be -27, but there's no 27 in the array. So I added this -7 in the array, and it goes on and on and on. So it's not going to work, right? Because I can make the equation right if I have more than 3 negative integers. So that could be an observation. If I have more than 3 negative integers, the equation cannot be working. So I need to check positive integers. So I wrote down 4, 6, 8. And if I call them I, J, K, AL should be 18. But since 18 is in the array, what if I add 18 here? So it looks working, but I, J, K can be like this. So I need AL as 32, right? So it goes on and on and on. So it's not going to work if I have more than 3 positive integers, right? And zero's working in easy way because it's only 0. So the observation can be like this. I can have negative integers at most 2 values, and I can have positive integers at most 2 values. And zeros can be 2 zeros or 1 zero, because 3 zeros are working themselves, so it doesn't need to be checking for 3 zeros. So at most we have like 6 values in the array, and then we need to iterating them by brute force because it's only 6 to 3. So we can check the equation works or not by iterating 6 indices, and that's it. So as I told you, after we find this operation, the solution is easy. So that's it. So let's move on to the fourth problem, fixed point guessing. It's about guessing the fixed point. And we need to read explanation. And I made an example for explanation. So we have like 1, 2, 3, 4, 5 as an array A. It can be changed like 4, 2, 5, 1, 3 by swapping some selected disjoint pairs of elements. So then the fixed point from this array will be 2, and the other elements are swapped by each other, and it can be swapped for only once. So we need to find fixed point by using queries, and we can use at most 15 queries. And since the n is lower than 10 to 4, we can assume that, we somehow need to use binary search because binary search can make the queries at most 14. So it's kind of, need to use binary search. We got that idea from checking the 15 queries and the value of n. So it's like the third problem. We need to find observation and then we can solve. And finding observation is very hard. And after that, solving the problem will be easy. And we have to think about why n is odd number, but we don't know before we find observation. So let's have a look, an example. So if we use query to L to R, we got the answer for it, and we can count the number of the number of values in the array in the range from L to R, and I call it ranged count. For example, we got 2, 1, 6, 7, 8, blah 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 blah, and I used if I use query from 1 to 5, I get 2, 1, 6. I get like sorted way. I get the answer as sorted way, so the answer will be 1, 2, 6, 7, 8. So I can count 1, 2 as ranged count because 6, 7, 8 is over 5, so we don't need to count them. And since I want to check the ranged count is even and the ranged count is odd, first we need to check on the even side. So if we have 2, 1, 6, 7, 8, the ranged count will be 2 and 4, and that's for 2 and 1. Or we have like 2, 1, 4, 7, 4, 3, 8, the ranged count will be 4. And since we kind of have idea that we need to use binary search, we need to find observation here. So when ranged count is even, we don't need to find any deeper binary search for this range because there's only even number of ranged count. And since the number can be only unswapped, they are all swapped. I mean, the even number, a b can be swapped, or a b, c, d can be swapped, or whatever. If the ranged count is even number, there's no answer here because the swapped number is same as ranged count, so there's no need to find an answer here. So we can save query count here. So answer should be when the ranged count is odd, because even is not gonna work. So I made an example for fixed point. If we have 1, 2, 3, 6, 7, the ranged count will be 1, 3, 2. And as you can see, fixed point is 1. So now we know that the fixed point only exists when the ranged count is odd. And I wrote down another example that is 1, 6, 7, 8, 9, and the ranged count is 1. Also, the answer is here. So we can find it. by using binary search. Like if the array is 1, 2, 3, 1, 3, 2, 6, 7, we got the odd number of ranged count. Now we know that, somewhere in the array from 1 to 5, there is a fixed point, which is answer. So we need to find the answer by using binary search. Like this, we can use recursive way or by using, looping them left, right. So we can use binary search from range 1, 2, and 2, and 3 to 5. And we'll find an answer from here. And that's it. Finding an observation will be hard, but the solution is easy. We can find, the conclusion is like this. We can find fixed point by using binary search, and the ranged count for the range for from L to R is even. We don't need to find the answer from it, and there's no answer. And the output from the range of L to R is odd number. There is an answer for it. There isn't, fixed point between L to R. So we need to find the answer by using binary search. We need to, divide them, and we can check, right? So that will be the fourth problem of this, round, and it's called fixed point guessing. And that's it. Thanks for watching the whole video. See you on next round. See ya.